Welcome to my report on the Week 5 reading. This week we began looking at magnetic fields. We looked at what causes a magnetic field, what a current is, and then the Biosurvey Law for a moving point charge. For a straight current carrying wire, and for a current carrying loop. The first two videos in this week's readings covered the concept of torque and the method for calculating the cross product. I'm familiar with the concept of torque from taking Physics 1 over the summer, and familiar with cross products from different math classes I've taken, as well as Physics 1. The content about magnetic fields, however, was entirely new to me. It's important to note here that magnetic fields are only produced when there is a movement of charge. We began by calculating the magnetic field of a moving point charge. The direction of the magnetic field B is the sign of the charge multiplied by the cross product of the direction of the charge velocity and the direction of the observation location. The magnitude of B is given by the formula seen on the right here. Combining these two, we can derive the Biosurvey Law, as seen here. The SI units for B are a Tesla, which is a Newton second per Coulomb meter. We then moved on to the Biosurvey Law for current. First, it is important to note that the current is a flow of charge. The idea here was to take a small length of conductor and measure the amount of mobile charge passing through a cross-section area of it. By measuring the rate at which this happens, we are in fact measuring the current passing through the cross-section area A. Using this information, we arrive at this equation for I, the conventional current, where Q is the charge, N is the number of mobile charges over the volume, A is the cross-section area, and VD is the drift speed. This value is measured in amps, which are coulombs per second. Next, we calculated the magnetic field for two different current-carrying shapes, a straight wire and a ring. For both, we followed a similar procedure. First, we divide the current configuration up into current-carrying pieces. Next, we find the magnetic field for a typical piece, and lastly, we superpose the fields to get one net magnetic field for the shape. By following this process for the straight current-carrying wire, we arrive at this equation for the magnetic field, where the observation location R is on the plane which perpendicularly bisects the wire. In the case where the length of the wire is much greater than the distance of the observation location, we can use this simpler approximation, which is proportional to 1 over R. Following the same procedure for the current carrying loop, we obtain this equation for its magnetic field, where the observation location is on the axis, which perpendicularly passes through the plane in which the loop lies. There is, again, a special case when the observation location is small compared to the radius of the loop, and the magnetic field can be approximated by this equation here, which is proportional to 1 over R cubed. At the end of the last video, we also briefly discussed μ, which is the magnetic dipole moment, which is analogous to the dipole moment from the electric fields topic. The hardest concept for me to understand this week was why magnetic fields are only produced in the presence of a moving charge. However, after reading the physics book page on moving point charges, I feel I understand the reasoning much better. This week's reading was mostly new content for me, and when I thought about it in the context of my own major, computer science, I thought about how the hardware in a computer must produce many different interacting magnetic fields, and I was wondering about how the components are designed to mitigate this. This concludes my report for the week 5 reading. Thank you very much for listening.